This question is asking us to find how many molecules out of a group are polar. And to do that, we're going to look at partial charges and dipoles. And then we're going to use the molecular geometry to figure out if those dipoles cancel out or if there's a net dipole left over. Because if there's a net dipole, then that means the molecule is polar, and if they all cancel out, that means it is nonpolar. So let's look at the first one. It's going to be OF2, and first off we need to draw a Lewis structure. And so we have F on each side of the O, and so we're going to go ahead and add a single bond on each side. And then using the periodic table, we know that there are 20 valence electrons in this molecule. So let's start off by making an octet on the F by adding 6 to each one to make 8 valence electrons, and we count them up and we get 2, 4, 6, 8, 10, 12, 14, 16 used, meaning there are 4 valence electrons left over. So we're going to go ahead and add those onto the central atom. And now that should add up to 20, so we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So now we've used all valence electrons, and this is a good Lewis structure. So now we're going to look at this, and we see that F has a higher electronegativity than O, meaning it's going to have a negative partial charge, and O is going to have a positive partial charge. So since F has a negative partial charge, then that means the dipole is going to be facing the fluorine with the tail of the oxygen. And we're going to do the same thing over here. So now we have our dipoles, so now it's time to construct a diagram of the molecular geometry. So we're going to come right over here, and we're going to say, put the O right here, and now we have to look at the bonding domains, and we see that there's 2 pair of unbonded, so that means we're going to have these right here. And then we see 2 bonded pairs, so we know that we have that and that coming down to the F. So this looks to me like it's a bent domain geometry. So now we construct our dipoles again, and we have these running this way because they have to point towards the F. And we see that they are not linear. They're not facing the same, are on the same plane. So that means we're going to have a net dipole that's running this direction. And since we have a net dipole, that means that this molecule is going to be polar. So let's go ahead and right over here to the side that this one is polar. So we can go up here and we can check that this one is polar. Now we come down to our next one, and we already have the Lewis structure made. So when we do the same thing, we know that the oxygen has a higher electronegativity, so all the partial charges are going to be negative. And this is going to have the positive charge. So basically do the same thing, and we have a dipole, and a dipole. So now we've made our dipoles, and the next thing to do is we're going to come over and construct our other one, and this one is going to be a trigonal plane. So it's going to look something like this. And now we put on our dipoles again. So this all of these have the same bonds, so the dipoles are all going to cancel out, making it non-polar. So we'll go ahead and right here, non-polar, and we're just going to leave that marked off because it's not polar. So coming down to the next one, Lewis structure's made. Cl has a higher electronegativity, so negative charge, positive charge. Draw our dipoles, and There we go. So now we come over here and draw our structure. So this one's going to be linear because it has 2 bonding domains and no non-bonding. So we have BE, CL. And now we're going to look at this and draw our dipoles again. So we see that everything on the central atom is the same, so these 2 dipoles cancel out and we're left with nothing. So this one is going to be also non-polar. So on to the next one. We continue the same process. Cl has the higher electronegativity. So negative, 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 and positive right here. So continuing, we draw our dipoles. Okay. And we see that this is probably going to cancel out again, but let's go ahead and draw our other diagram anyways. So because this is 4 domains of all 4 bonding, we're going to have a tetrahedral, which is going to look something like this. And we have Cl, 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 and Cl. So again, drawing our dipoles. We see that they do in fact cancel out because they're all the same. So again, we have a non-polar molecule. Okay, on to the last one. So this one's a little bit different. This is a resonance hybrid, so we have 2 Lewis structures, but it's pretty much the same thing. But since these all have the same, they're all the same atom, we're not going to have any partial charges on this one. But we can still look at the central atom, and we can see that there are 2 equal domains that are bonding, and then we have 1 non-bonding pair. So now what we're going to do is come over here and we look at it and say, well, 1 non-bonding pair and then 2 equal bonding pairs is going to give us bent geometry. So now we know we draw our dipoles, and we see it's similar to the very first one, so we're going to have a net dipole going down, meaning that this molecule is going to be polar. So then we come back up here to the top, and we check this one off as polar. So we see that, to answer the question, 2 out of the 5 are polar, being OF2 and O3. So a common mistake that I think confuses a lot of people is, first off, they don't even get their Lewis structure right, which is definitely going to throw off the whole problem. And also, most people just don't understand the molecular geometry, so they just can't picture it in their head, and then you'll never be able to figure out if the dipoles cancel or not. So, yeah.